Alright, can you start? No? Because there are a lot of things to cover in this segment. So if you remember on last this class, we are discussing all these portions of our discussion leading towards DES as we have mentioned. Most probably by tomorrow we will start with the DES algorithm, and you will observe that all these prerequisites to DES is what we are doing over here, starting with the S box, the P box, the circular shift, the swapping operations, all will be applicable at some point. But keeping in mind the process that is involved in DES, the major part of it is something called as a function or the basic structure of DES. For that, we need to understand something called as Feistel algorithm, alright, or Feistel cipher. So today's discussion is going to be on that. But before that, going to there, I wanted to recap on what we had done on previous day. And one of the important things that we have done on last day's class was a product cipher, where I told you two very important definition, and one was the diffusion, the other one was confusion. And the meaning of it in general is that by somehow we need to make sure that the ciphertext and the plain text are hidden from the intruders, and also the ciphertext and the key should be hidden from any attacks, possible attacks from any intrusion, right? So that's the basic observation. And keeping that in mind, we observe that we also have termed something called as rounds, where rounds indicate a possible combinations of multiple S boxes and P boxes, such that for each and every round, whatever be the output of one round will be fed to the next round, and add on a more number of rounds. The process will be more and more random to make the data to be more and more random. And I told you that for most of the cases, the example that we took, I think if you remember last day, was an example where there were two rounds only, round 1 and round 2. But if you observe the diagram, they are absolutely similar, keeping one of the middle element as the middle text, which is a black colored box, which is an intermediate stage in between. Now, as I said, that this is just an example with 8-bit data. Now, in case of DES, you will find the same thing will be repeated, but with 64-bit data, and the rounds will be total number 16. Alright? And also you can observe that this is a very preliminary and a very rudimentary structure, we can say, because here there is no circular shift, there is no swapping operations, nothing has been used as much. This is nothing to do with DES as such, because all those features will come in when we are doing the original DES. And in that when we were explaining it, I told you that the S boxes and the P boxes, they follow the same rule as we had discussed previously. So please go through the previous lectures and the materials to understand, those who were absent on last day's class, to understand that. Now, keeping that in mind, now we are looking at something called as Feistel cipher. As I said, this becomes a very important factor and a part of our DES. If you are stuck in any of these steps, you won't be able to understand DES. That's the problem. And if you are not able to understand DES, possibly you won't be able to understand AES, which is the advanced encryption system, which will come after DES. Alright, the loopholes of DES will be taken care of by AES, which will come later. So please concentrate properly and understand each and every step of it. Alright. So as we are discussing this one, that the modern block ciphers usually have the two types of product cipher. One is called the Feistel cipher and the other one is called non-Feistel cipher. Remember that we are discussing Feistel cipher. Why? Because DES will use the Feistel cipher. But while we are leading towards the AES, you will find the non-Feistel ciphers will be used. And what is the difference between the two? You can mention over there. Ciphers that have both invertible and non-invertible components, we call it in terms of Feistel cipher. And if you have something in terms of only non-invertible components, then we usually call that as a non-Feistel cipher. So for the timing, we are not going to discuss much about non-Feistel cipher as of now. We'll see mostly on the Feistel cipher. So this is the basic structure of a Feistel cipher, as I was telling you, that the preliminary diagram, the previous diagram that I showed you of the 8-bit and the round 1 and round 2, that diagram that I was showing you, that this diagram I'm talking about. If you observe that there is very simple way of dealing with the permutation box as well as the S box. But naturally you can imagine that this is very relatively rudimentary steps that is being followed. So to make things a little bit more randomized, what happens is that we will add some kind of a mixer as one of the block, as you can show, as it's been shown over there as a yellow box. And if you remember, the very important function that I told, I think I started off in the last class as well, that there is a function of f of k which will be used. Now, what is f of k? It's a function which is directly related to the key. Alright, so it is a function which is dependent on the key. So, whatever the key you are generating for each round, the function will behave with respect to that particular key. So, you can imagine that whenever that XORing is happening with the data, you can see, observe over here, P1 is nothing but the plain text. So, the plain text is coming over here. Now, suppose this is my first round 1, suppose, for example. So, this will be my K1, right? Now, this, when K1 is happening, this for based on with respect to this K1, this F1 will be F of K1. Now, similarly, for 16 such round, there will be F of K16. So, for each and every round, this function will play a very important role in making the randomized data. Right? So, that's what we are going to discuss, and you can observe here that why we can use such a function without troubling the encryption or the decryption process. It's given in the back, at the bottom of it. So, you can observe that what is C1? C1 is over here. C1 is very simply P1 XOR F of K, where F of K is the function. Now, in the decryption, when you are doing the decryption, so that is C2 over here, you are sending the data C1. So, the C2 plus F of K, you can see that the decryption also, we are using the same function. Remember, this is only generic discussion. Now, when we go for round 1 and 2, each and every time the functions will change. So, suppose this is what we are talking about, the generic discussion. So, F of K will again be added over here because the operation is repeating over here. So, C2 XOR Fk. Now, C2 is again divided into C1 XOR Fk. Why? Because this C1 is assumed to be same as that of C2. Because we are assuming that's basically where I would say as an analysis, it's a fault. Because if you are saying that this is a transmitter and a receiver, you are supposed to get some kind of a noise in between. Right? Because this transmitter is somewhere over here and the receiver is something over here. But what we are assuming right at this point with this particular subject, that there is no noisy environment in between. Understood? So that's why what happened? So that's why there is no such noise that is incorporated over here for our analysis. Because we are mostly focusing on the data, how it has been encrypted. That is the part of this subject. But suppose you are doing this in your wireless communication subject, then there must be a noise that should be taken into account also. Or in general, if you are using that in a generic communication system, you have to add a noise. That's a separate discussion anyway. So now C1 and C2 are same in that case. So that's why we can say that C2 is equal to, so this can be given as C1 plus, so C2 can be given as C1. So C1 plus C1 XOR F of K. Again, C1 is given by P1 XOR F of K. So that has been mentioned over here. And if you remember, I told you that the exclusive OR, one of the rule it was given that when it is given by XOR plus X plus XOR, it will always be 0. So this part yields us 0. So basically what we are observing that this P2 is equal to P1. So what I mean is that the output received data will be same as P1 even if we are using a function F of K in between. Understood the process? The function that we are trying to use is making the data randomized. But that particular function and the XOR operation is making a process where it is a relatively invertible process that we are observing, and we can claim that whatever we had fed in the system as the plain text, we are getting back the same plain text as a decryption. So what the meaning is, you know that the transmitter is sending a data which is purely a raw data. The receiver is bothered with the final data. In between, if someone is trying to intrude, they will get some randomized data based on the functions being used. But for the overall system, it won't change anything because the input and the output will be the same. So that's being shown over here. Got it? So this part is very important, this function. Now, how you are going to define this function is entirely dependent on you. Alright, so that's how the algorithms are defined. So that is where you will find that in DES, certain rules are applicable on this F of K. It won't be, this is the first of the assumption that we have to use a function which is dependent on key. But now you will find the next slide. So this is just an example of it. I'll come back to this example, but let me just continue on this. You can observe that small little difference has been made over here, and that's where we call it as a PSL cipher. I'll come back to that example after this. If you observe over here, the same diagram as I had mentioned in the previous slide is mentioned here, but there are certain small changes have been made. One of the changes is that the plain text which was here as P1 has been now been divided into L1 and R1. So there will be a splitting somewhere. Remember the word splitting we had used in the last class itself, one of the tools that has been used. So basically if it is a 64-bit data, as in DES we are going to see it, so you have to divide that into left and right. L1 and R1 stands with left 32-bit and right 32-bit. And for this particular scenario, what they have done, see the arrow and you can understand very clearly that what is happening, that the function is defined not only with key, but a portion of the plain text. It's not f of k, but it's a function of f of r1 comma k. So the function is now defined in a way that a portion of the right side bit and the key will also form certain action. This function is nothing but a XOR operation, nothing else. But earlier it was only the key directly getting XORed with the plain text. See the difference. If I go back, it was here, f of k is nothing but a function where key is coming, okay, and it is getting XORed with the plain text. We are getting some random data. That data is being fed to the next system. Like that it was going on. But if you see the difference over here, now the data itself is split into two, left and right. And the left is kept undisturbed. You can see over here, it is left undisturbed. Whereas the R1, this R1 is somehow affecting the function, and that affected function is getting XORed over here. Can you understand the difference of the PSL cipher? The preliminary diagram that I showed you is the application of the function, but now the function is now not only based on the key, but it is now part of the data also is affecting the function to use. So now if that is the case, you can see the final data, the encryption data also will have two parts, L2 and R2. Unlike to the previous case where it was only a P2 or I think P1, C1, sorry. It was only C1. So unlike to the previous case, here we are having two different set of data, L2 and R2. And in the opposite end, you can see the receiver side also, we will have certain kind of R3, which is nothing but the portion which is over here. See it carefully. This is nothing but the C2, which was there in the earlier case. The same data, the same encrypted data is now divided in two halves, L3 and R3. And R3 combines with the K, which may be K1 or K2 or K3 or K16, whatever it is, and that forms L4 and R4. Any doubt with this part? How it is different to the previous diagram? Previous case, it was only dependent on the key. But now it is dependent on the portion of the data, especially the right side of the data, and the portion of the key, which is getting XORed internally. That output is now XORed with the left part of the data, as you can see in the diagram itself. That final outcome is the encrypted data, at least if this is only one round we are considering. So the L2, R2, the combination of L2 and R2 is basically my C1. Understood? And in the reverse direction, it is the same process, except that the f of R, which was R1 in the transmitter, has now been R3 because the same logic, because this is my input and the portion of the right side of the input has been fed as the input to the function. Am I clear with this? Because this forms the basis of DES. If you are not clear, you won't be able to solve the questions on DES or even understand the DS. Because remember, this is we are doing with respect to only single round. We have to repeat that for 16 such rounds and along with certain other actions. Any doubt with this? Anyone? Alright, let me go back to the previous slide to explain one of the example that I was talking about with respect to the previous case when we don't have that key to be added. So you can see in this question over here, the plain text and the cipher text are each of 4-bit long and key is of 3-bit long. Alright, so the plain text and the ciphertext, so 4-bit long is the data and the key is of 3-bit long. Now what is happening, and assuming, so now this is the function f of k1 I was talking about. See here, this is with respect to the previous one. We are making some condition on f of k. What is the condition? Assume that the function takes the first and the third bit of the key, interpret these 2 bits as the decimal number, squares the number, and interprets the result as a 4-bit binary pattern. Now this one that you are looking at, the second point, is a condition for generating f of k, imposed with respect to the first diagram that I given you over here. This one. Alright. So the condition is that the first and the third bit will be considered as the function takes first and the third bit of the key, interprets those data as a decimal number. So let's see one of the cases. The original plain text is having 0111, 4-bit at a time, because plain text is 4-bit. Now as per the rule, the first and the third bit is considered to be, so first and the third bit, first and the third bit, okay. Now this is the plain text, sorry, key is 101. For the key we are talking about. So the key is 101 because key is 3-bit. So the key is given as 101. So which one is the first bit? First bit is 1. Second and third bit is 1. So basically you are looking at 1, 1. Now convert that 1, 1 to the binary. So binary 1, 1 is converted to decimal number, which is 3. That's the function. Now convert that 3. Now 3 to square. You can see the next line. Convert the 2 bits as decimal number. Square the number. So 3 is taken square. So 9. Interpret that result in 4-bit binary pattern. Now 9 is now interpreted as 101001. So what I did? First of all, I have 101 as key. First bit and third bit we are considering. Okay. So that digital data, the binary data is now converted back to decimal number. We take the square of it. Whatever the number we are getting, we are converting back to digital format or binary format. That number, like in this case is 101, is considered to be the key over here. You can see. So f of k, the function that I was talking about, is a value which is 1001. Now how this 1001 is generated is based on the assumption that we are making over here. Now it can be anything else. Suppose for example you design an algorithm where you will not take the square. You will only take it as the decimal equivalent to the value, binary value, that is 3, and you might take a cubic expression to it. Suppose you take a cube. So 3 should be cube. 3 cube we will take. Then we will take a binary equivalent to it. That may be another function. That may be another function. Right? Or you can take the complement of the data. So you can take a complement of the data of the binary set, and that can be another key, and that will be used as a function. Anything can be done. This is one of the example of f of k. But if you observe carefully, since we now know the Feastel process, it is only dealt with respect to the key. It is nothing to do with the function is nothing to do with the data. Am I clear with this? So this example actually shows us that this will be my encrypted process, and the decryption wise also we are getting back the same data, because you can see the plain text was 0111 and we have got back the 0111 over here. The proof that I gave you in the previous slide is being verified over here. This 0111, this was straight as the P1. This is my P2 which is getting out. So even if we are using a certain function, okay, we are using certain function, the P1 and the P2s are the same, which we had proved over here, in fact. So same thing we are interpreting with our live data with 4 input and 3 output, like 4 plain text and 3-bit key. Any doubt, anyone with this part? How we are doing, why we are doing it? Anything, any question on this? First, we are trying to make sure the randomized data in each round. So we are observing a process in which we can make that random data to appear. First, we started with a generic observation where there is a generic function f of k, which is a function dependent on k and certain condition. To understand the condition, this example was given. in which the data first and the third key bits of the key are considered to be the binary number, convert it to decimal, and we take a square of it and we reconvert back to binary. That is the logic for the function, supposing one of the logic. Using that, we are doing the process and we are trying to find out what is the ciphertext and what is the decrypted text as well. And we are seeing that the input and the output are the same. But as I told you, that this is only dependent on the key. Whereas the Feastel cipher over here, which is more of the realistic process, in fact, because the earlier one, if key someone knows, they can break they can decipher it quite easily. It is only dependent on key. But here you can observe that it is dependent on both key as well as part of the plain text, not the full plain text. So that adds to the randomness of the process. So that is basically what the Feastel cipher is all about. So let's see why, even in this case, although if we are doing this as L1, L2, is it still relevant that the P1, that is the plain text which we are feeding as an input, comes out the same as that of P2, even if we are doing all those changes in the data. So let's see that. So this all is not needed. So suppose you can observe over here, that's one of the small example that we are giving. Very simple. Assuming L3, please follow this carefully. L3 is equal to L2. Because we are assuming that the encrypted data, that is C1, is equivalent to C2. Because there is no noise in between, that like I said. So basically we are assuming that L3 is equal to L2 and R3 is equal to R2. Okay. Now R4 is equal to, R4 is where? R4 is over here. So R4 is equivalent to R3, because you can observe that a line, just observe this carefully, R3 directly goes to R4. So basically we can say R4 is equal to R3. R3 is again equal to R2, so that is again same. And R2 also is equal to R1. Can you see the change over here? Can we write this? We are assuming R3 is equal to R2. That means this right side is equivalent to this side. Again, R2 has a direct connection over here. So R2 is basically equal to R1. There is no change over here. Directly R2 is coming over here. See, line. There is a feed over here. L2 might be varying. L2 might be varying with respect to R2. But R2 as such doesn't matter. It doesn't matter. Just go straight. So R1 is equal to R2. R2 is equal to R3. R3 is again directly going to R2. So this is what we can do. So basically what is indicating over here, the right side of the data is remaining intact. That in fact is a flaw in the process. The right side of the data, if you observe R1, R2, R3, R4, they are all the same. So if someone interprets any one, they can interpret a portion of the data itself. Is it not the case? If you know the process that the right side of the data is same all throughout, then you can assume a portion of the data is already known to us. So we have to just interpret or find the process, the left side of the data. So that's in fact is one of the drawback of this system. We'll see that how it can be converted or changed. So if you observe there, now we are writing it L4. So let us try to interpret L4. L4 is given by, what is L4? Can anyone tell me just by looking at it? L3 over here, XOR to F of R3K. F of R3K, from the diagram very clear. Now L3 and L2 are same, so we are mentioning L3 is equal to L2. XOR F of R2K. Why we can write F of R3 comma K is equal to F of R2 comma K? Because R3 and R2 is common, that's why we can write it. So we can write it this way. Again we can say L2 over here is dependent on L1 XOR F of R1K. And in the same manner, we have just arranged it in terms of F of R1K, because R1 and R2 are again same. That is what the logic is. Because you can observe again that this 2 XOR will have a 0. So basically what we are observing, the L4 is becoming equal to L1. Already we have proved R1 is equal to R4 based on the structure of the algorithm. And we are now also proving that L1 is equal to L4. So if you combine both L1 and R1 for C1, this is equivalent to L4 R4 C2. Understood? Last time what we did, same thing we are doing. So the P, rather this is P1, it should be P1 rather, and this should be P2 in fact. So the plain text which we had, a portion of L1 and R1, with this we are proving that even with this kind of a function, f of k, f of R1 comma k, or we are modifying it with respect to our need, the rest final calculation shows that whatever we are giving as an input to the system is same as that of the output. So the interesting part is that irrespective of which function you are using in between and what logic you are using in between, even if it is a black box to you, it doesn't matter because the input and the output will always be same. You can add different logic to it. You can interpret in that way, but even that can be proved that final and the initial and the final part will be the same, and that's basically what we need. That's basically what we need. We need to secure both the transmitter and the receiver side data. So in this particular example, we had shown that how this can be interpreted. Any doubt over here? This is equivalent to the previous one only, except that f of function has changed. The Feistel function has changed. Right? Now you can observe this is with respect to cipher with 2 rounds. Alright? The discussion whatever we did up to now it has 2 rounds, and this is a little bit modification to the previous one. Can you see the difference compared to the previous diagram? Anyone? Can you interpret the difference? Yes. So this is what is being used over here, which was not there in the previous diagram. In the previous diagram, it was after the mixture we were getting C1, the encrypted data. But here if you observe, there is a swapping process that is going on. What we are going to do in swapping process? Left will become right, right will become left. Simple as that. Over here, you can see right is shifted this side and left is shifted this side. So you have suppose a 32-bit data, 16-bit is L part, left part, and 16-bit is for the right part. This left part 16-bit will be converted to a right bit, and this right bit will come back to the left bit. Simple as that. So that is an add-on feature to make things more randomized. That's it. Nothing to do with anything else. That is why the tools or the processes I told you in the previous class, that these are the fundamental utility tools which will be used in some place later. So you cloud this part. We are generating directly L2 and R2. But now in this particular redesign or modification of the Feistel, this is called the final design in fact, we are adding a swapper over here, where the left and the right has been swapped. So basically your L2, which is over here, which is an intermediate L2 I'm talking about, is nothing but R1. See over there? L2 is nothing but R1 and your R2 is nothing but some elemented value of L1, some modified value of L1. So that is an add-on feature for the final stage of Feistel. But ideally, this swapping and the final stage that you are looking at is absolutely the same to that of DES process. In DES, what you will find that these are called as Feistel rounds. This round that you are looking at, they are called as Feistel rounds. Because this process is Feistel cipher, we call it. So there will be 16 such Feistel rounds for DES. So every round you can observe there will be a permutation. After that there will be a function which will make sure the randomized ORing and that thing happens. Then we have L2, R2 or left and right as a cipher text. This gets swapped. Now whatever we are getting, that will be fed as the input to the next round. Understood? Now that data, again you can see over here, now this is interpreted with respect to F R2 R2. Now this R2 is nothing but this, which is the swapped version of it. Am I making sense? Are you able to understand, recollect all the process? Because this is what the basis of the DES algorithm is. So I might skip portions of DES because if you are comfortable with this, because in DES, as I said, it's a repetition up to 16 rounds. 16 such Feistel rounds will happen. But not only that, there will be some changes in the key. The key won't be given as directly a 16-bit or 32-bit. There will be some change there also. So that's different discussion. But this is what the final stage of Fiesta algorithm is, right? So this is the interpretation of it, that using the swapper also, we can prove very effectively that the final initial and the final destination will be the same. So I'm just keeping this, I'm not proving this because this is same as that of the previous one, like I said, and you can interpret from the diagram itself how we can prove that L6 is equal to L1, L6 is over here, and L1 is over here, and also we can prove R6 equal to R1. So R1 and R6. So same discussion that we did, even with the swapping operation, I'm keep on telling you this, even with the swapping operation, even with any other modification of f, the function, the result will remain the same. So ideally in this, what you are observing, that L1, R1, which is nothing but the P1, is equivalent to L6, R6, P2. So I keep this derivation for you to just discuss, like go through later and find out that this is the same as that. Or you can in fact prove it on the go itself, and you can find it out very easily that how it is to be done. This is same as that of the previous explanation that I gave it. Same thing. Only the swapping you need to keep in mind that how that has been happening. Right? So basically where we stand at this point, that the product cipher we know that there are different rounds. In those rounds, there are certain permutation that will take place, and each of those rounds might have something called a Fiestel process, in which there will be a function which is dependent on the portion of the data, that is the plain text, and a portion of the key, or rather the full portion of the key, and that will be taken care of for each and every round. And as we go on with the rounds, the same thing will be repeated again and again. Got it? Done. So now we come to, as I said, we'll not discuss the AEC at this point because we'll finish the DES, then we'll come back over here. So non-Fiestel cipher, as I said, is very important with AES. We'll come back to this. Let us not discuss that over here. We'll make things a little bit more difficult for us. Now we come to the first slide of the DES. As we have been telling you for long, I've been telling you for long. So DES, again, as I said, it is the symmetric key block cipher. Even you will find the AES will be an asymmetric, although it is an symmetric block cipher. But in advanced encryption system, AES is also very similar to it. Very similar to it, except the logic is more or less same, I would say, not exactly. But the most important feature is over here, in case of DES, we use only 64-bit of block data. Whereas over AES, we are going to use almost 128 bits. And another thing is, you can see over here, it was developed in around 1977, if I'm not wrong. 75 and all. Alright, so that is where it was developed. Whereas AES made a standardization by NIST in the year 2001. So as early as 2001, it got a final certification that yes, this will be the standard encryption key for most of the networking systems. So that's why it is more relevant, and it has still, up to till date, there is no one has break the code. Like anyone intruders that broken the code of AES, it never has happened. That's what the textbook suggests. Alright. So let's discuss AES later. First, let us conclude the DES portion that we have. Now, mainly, you can see the last few lines, which I think is very important before we start off with anything. Criticized severely for two major reasons. One is that we have the key length which is of 56 bit. So that's one of the problems. The key length is small. Why it was prevalent in 1975 and 77? Because at that time, we never had that much of high processing computers. We never had multi-processing system, multitasking system. Alright, so that time, 75, 70, you see the time frame. Historically, that's what the truth is, that people thought that this might not be cracked anywhere. Because you will need so many systems and so much fast processors. At that time, there was no invention of that sort. So if people were sitting pretty, wow, this is fine. But later on, with the advent of VLSI techniques and more like the processing speed, higher end processing speed, it was found out that this 56-bit deciphering or the key generation is not a very adequate one, because people can actually decipher. In fact, it was proven, I think, if I'm not wrong, with my the study, it was like in 120 days, it was found out that all these keys, whatever the combinations of keys in DES, it was deciphered properly. And if you know the key, you can know the text itself. So there is no security as such. So that can also be done. Although the processing speed might be very high, there will be number of processors which you require more. But for a system like nowadays, there is nothing like that. You can have multiple system which has very high configuration and you can work on it. So that is why DES is ceased to exist now. That's why people use AES. That's the major difference between the DES and AES. That's why instead of this 56-bit, we will use 128 bits. Okay, and that's the basic important part. And the second part, you can see that critics were concerned about some hidden design behind the internal structure of DES, which was not disclosed at that point. So people were a bit reluctant in using that black box thing, like how it is working. Later on, it was divulged and it was given the full clarity later, but that was one of the reasons. So let's see. Now, as I said already, we have discussed about the basics on the Feastel cipher, so we can skip a few slides. So this is the basic block diagram. I think no one will have any doubt understanding the block diagram over here. So we have 64 plain text. This you please make a note. I've been harping all throughout 64-bit input as a plain text, and you have a key which is of 56-bit. Please understand this carefully. This number of bits will play a very important role later on. So please keep in mind, don't change it, don't alter it, nothing you do. Okay? So that's all the process, very simple, the same thing. But this DES cipher will have multiple such Feastel cipher rounds. So I think I'll give you a diagram first, then I'll come back to all this. Let me just give you the complete diagram first, just to show you. This will be the complete structure of a DES cipher. I'll come back to this later also. But if you can observe very carefully what we have studied right now, we have an initial permutation, leave out for the time being, we'll discuss later. This is a function. Can you see the function over there? I have marked it. This is nothing but a Feastel function. F of R, K. That's why I wanted to show you. This is a swapping operation over here. Can you guess it now? So this is basically round 1, round 2, each and every case. These are all Feastel rounds which are repeated 16 times. That's what I was telling you a while back. Alright, so that's why we can skip few things if we know the previous things properly. Okay, so I'll come back to this later. Let me just start off with the portion that is there. Alright, so this is the part. So the encryption process is made of two permutations, which called as initial and the final permutation. So why it is called? You can see from the basic block diagram. So we have the 62-bit plain text coming over here, and you have two such blocks which are different to that of the Feastel round. One is called initial permutation and the next one is called as the final permutation. So between initial and the final permutation, you have 16 such rounds which are placed. And all those round 1, round 2 which you are observing, they are all Feastel rounds. Which in between that Feastel round, you have the function, you have the swapper block in each of the cases. Right? And you have the keys over here, which is 56-bit cipher. But to make things happen, we will use 48-bit instead of 56-bit for the calculation purpose. And for that, you need something called as round key generator. So key generation, up to this point, if you see the Feastel discussion that we have done, key was not taken care of. Key was like total number of keys coming and it is getting XORed with the data, like the portion of the data. But now in this DES, we have a separate block over here which will try to randomize the key as well. Understood? Previously, data is coming, we are trying to make the data random by using the key. But now what we are doing, the data is anyway randomized, but the key generation is also randomized. So we are adding a layer of security to the process. Okay, so you can see there that let the initial permutation of it. So without looking at the text, maybe I'll just show you this one, which will be easier for you. So you can see the left hand side, this one is called as the initial permutation table. Is it not what we have discussed a while back? while we were discussing long back when we started off with the circular shift and all, I showed you table and I told you that this is the output table, a standard output table with the input and output relationship for the P box. Remember I told you. So this left hand side, if you observe, remember the 58, the 7th output, this table I have shown you previously also. So this is my initial permutation. And the final permutation will also have certain elements which are there, given there. Now, as I said, this is only one of the standard ways defined for DES. If you ask me, sir, is there any other way we can do it? Yes, we can do it, but that won't be DES algorithm. That can be something else. So that's why we are going to follow mostly the standard table, which is given over there. And the respective diagram. Remember the numericals I did? If you are given a table, from that you have to back calculate to the combination. So if you observe that the initial permutation is given over here. Can anyone relate to that? We had done with a very small example with 8-bit, how to draw the P box. Remember last day we had done a numerical on that. Same thing we are doing. So this initial permutation, so that is basically my permutation table. This is my permutation table and this is the configuration. The top one is giving us the initial permutation of a P box, whereas the next one is giving us, after 16 round, the final permutation over here. Alright, so that's how. In between 16, there are 16 such combinations. 16 such combination in between. Right? So the initial and final is what we only need for the timing. So these are the two combinations. So keeping that in mind, let us stop with this example and let us finish up our discussion. So let's take an example to find out that how this can be done. We already had done it, in fact, but still it's a question. Find the output of the final permutation box when the input is given in hexadecimal of the value that is given. Alright. So if you see the solution directly, it's given over there. So what the question is that if this is the input we are giving as a 64-bit, what will be the output based on the final permutation table? So you can see that what we have done is, basically we have converted that all into digital bit strings, like binary bit strings. And in that you are observing, when you go back, so what I did, it started from 002. So we have done this way. 0002, so 000 means 0000. This is for bits 1 to 4. Then we have like that. And you can observe this 1 is present over here. So that's been mentioned over here. There are only 2 1s which are present in bit 15 and bit 64. Other than that, everything is 0. Now, why we are doing this? We are trying to find out what will be the final outcome. So this is my 15 and this is my 64. What is my final permutation table? Final permutation table. Which one is my 15th bit? How do I read this? How do I read this table? Index, the 15th index of the table will indicate the input that is connected to it. We go like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15th output will be the 63rd input. That's how we read that table. Remember last class. What is my 63rd bit? The 63rd bit, if you see in that order, if you go, it will definitely be, you can see over here, bit 15 is becoming bit 63 and bit 64 is over here. Is the 25th bit. So the 25th bit, you can go one by one, and if I mark it over there, so you can check 1, 2, 3, 4, like that we go 4, 8, 12, 16, 20, 24, 25th bit. See there carefully. 25th bit is what? It should be the 64th bit of the input. What is the 64th bit? 1. That's why it is 1. Confused? I'll repeat once again. This is my final permutation table. How do I read the table? This 40, what does this indicate? First output is connected to 48th input. That's how we read, right? Remember the previous day we did that. Similarly, you can see here in the same order, this is my 15th output connected to 63rd input. And here, 64th one, last one, is connected to 25th. So the output wise, 25th element is nothing but the 64th element, whereas the 63rd element is present in over here as a 1. So what we are mentioning over here is that based on the permutation table, the final permutation table, the input and the output will have a different set of data. This is nothing to do with the combinations of the in-between steps what has happened. It is just a question on what the input we have given with respect to the table, how it has converted to a different data. That's why I told you, keep on telling you, please go back to the previous lectures and the materials I uploaded, and I constantly had given you an example that how to read this table. Because remember, this table is nothing but the relationship between input and output. Index is showing us the output, how it is connected to which input. So if you are not able to comfortably understand that, you won't be able to solve any questions. Right? So that's all for the time being. So you can see the initial and the final permutation box, they are inverses to each other. We can get that back. And you can see the last line, which is most important, that they have no cryptographic significance to DES. As I said right now, this is nothing to do with DES algorithm. It is just that two permutations are used to make the data a little bit scrambled, and those data, whatever you are feeding in, it should come back in a different order. That's it. So that is nothing to do with cryptography. So that's why this is nothing to do directly with it's just a calculation based on the table, how you are rearranging the data. So please follow this example too, and then we'll come back to next day and we'll continue from the rounds and how we can do it.